Functionist should not be something new, right? The way the book defines it is always, I think, a little confusing, but anything in the domain is set to the anything in the range, but here's the big thing. Everything in the domain has to have a unique element in R. Short version of that, all x values are different. Right? Right. And hopefully you know that the input values are the domain. Hopefully you know that means that in a normal equation that's talking about the x values, and the output values, what you get out, is the range. That's your y values. Ready for some messy writing today? Yes? Domain and range. We talked about domain and range a lot last year in Algebra 2. Every time we talked about a graph, we talked about the domain and range. The hard part now is we're going to put all that together, all those types of functions, all at once, and say, what's the domain and range? So, again, the reason I printed these out for you is because all these lovely pictures, I didn't want to make you have to draw them all. You learned all the way back in Algebra 1 a really quick way to tell if something is a function by just looking at the graph. Which one of these is not a function? C, because why? Yeah, the x values have to be different. So if I draw a vertical line right here, this has 3 of the same x values. And if you notice in both of these, no matter where I draw a vertical line, that x value would only go through each graph one time. So remember the vertical line test. Again, I just kind of summarized that for you here. That if y is a function of x, then no vertical line will pass through the graph more than once, because that's the definition. If no vertical line passes through more than once, that means all the x values are different. Yes? Memories of this? Concrete memories of this, not just blurry, vague memories of this. All right, domain and range. Today we're going to kind of do domain and range, maybe with looking at graphs more than just algebra. But the goal of this is in the next few days, by the time we finish a few sections, you're going to be able to give me the domain and range without graphing it every time. But today we'll kind of do a little bit of both. The function is the square root of x plus 2. Does anybody remember what a square root function looks like when you graph it? We better just make an xy chart then. Give me a good number I could pick for x in this problem. 0. I find 0 to be a terrible number to pick. Because if I pick 0, what am I going to get? The square root of 2. I don't want to graph the square root of 2. We could graph the square root of 2. I just think it's not a good one to pick. If we pick 2, I think that's a good number to pick because 2 plus 2 is 4, and the square root of 4 would give me such a nice number, right? What else could I pick? Negative 2 would be a great number to pick. Because if you plug in negative 2, you get the square root of 0, and the square root of 0 is 0. Negative 1 is a great number to pick. Because although people forget a lot, 1 is a perfect square number. So when you plug negative 1 in there, you get the square root of 1, which is 1. And 7, and we'll stop after 7 here. 7 plus 2 is 9, so the square root of 9 is 3. When we're talking about domain, we're talking about what x values am I allowed to have. And so I've always said the best way to think about domain is to think about what you aren't allowed to have. What if I picked negative 4 for this problem, for x? That would be a problem, right? Because if I plugged in negative 4, I would get the square root of negative 2. And although we know that's just I radical 2, we don't know how to graph imaginary numbers. So we can't pick a number that would give us an imaginary value to graph. What is the smallest x value I would be allowed to pick for this problem that wouldn't give me an imaginary number? What was that? Negative 2, and we picked negative 2. Do you agree 0 is the smallest number I could ever get out of that without it becoming an imaginary number? Yeah. We're going to come back to this, but that has a lot to do with my domain and range. Let's graph this if we can have some vague memories of what this graph's supposed to look like. In section 1.3 in this chapter, I forget what it's called, but I like to call section 1.3 a library of functions. Because in your little brain, you should have this little file folder. Ever watch that SpongeBob episode where he has all the filing cabinets and he goes through and files? You should have a filing cabinet, and one whole drawer should just be functions that you know. And in section 1.3, we're going to go through that library of functions that you're supposed to have in your brain. Yes. He is trying to find his name, but I'm saying library of functions. So if I graph this, I'm not going to graph 0 squared root of 2 because I don't want to graph that. But if I graph 2, 2, negative 2, 0, negative 1, 1, and 7, 3, Sean, what do you remember the shape of this graph is supposed to look like? A half of a parabola on its side, which means this should not be a really jagged line. It should be very smooth. It's half of a parabola, because if we graph the other half underneath, it would no longer be a function. It would fail the vertical line test. So it's always half of a parabola on its side. And it's really easy to do domain and range when you have a graph, but I wanted to kind of go back to the equation at the same time here of doing domain and range. The domain is the x values, meaning where do my x values start or where do my x values stop? And we said earlier, just based on this, that we knew negative 2 was going to be our smallest x value. And look at my graph. It starts at negative 2, and it's just going to keep going to the right forever. So could I say my domain is negative 2 to infinity? I like interval notation. I'm going to use interval notation. Your book uses interval notation. You can also use set notation if you prefer. So I just want to show you on this one, just so you can see it. Set notation means for the domain you would say x such that x is greater than or equal to negative 2, and then you close those little brackets. That's another way to write domain. That's the way your Algebra 2 book did it a lot. I don't care which way you do it, as long as you do it correctly, one way or the other. But I like interval notation. The range is the y values. What are my y value restrictions? Again, with the graph, it makes it really easy because, Sean, what is the lowest y value I'm ever going to have on this one? 0. There's never a part of my graph that is below where y equals 0. And am I going to get all these y values up here eventually? Yeah, because this is going to keep going forever, and will keep getting taller and taller and taller. So we're going to start at 0 and go up. So could I say from 0 to infinity? Just kind of throwing this out here. If you didn't want to graph this, 4 square root equations to find the domain, you could just set what's under the radical greater than or equal to 0, because every time 0 is the smallest number you're allowed to have. You can't have a negative, and solve it, and it will always give you your domain in a square root problem. Now that changes that's still not going to change the domain. But if there's a negative on the outside, you're right, then it would change our range, because now that would be the bottom half of that parabola. And we're going to talk about that. There's a whole section on transformations in this chapter too, and we're going to talk about remembering what all those rules mean. For the range, I always say, look at your domain and then look at what the y value is. And look right here. My domain starts at negative 2, and look at the y value that goes with it. It's not a coincidence that the y value is 0, and my range starts or stops at 0, depending on how you look at it. Every time that's going to work. So if you know what your range is, you can look at, if you know what your domain is, you can use that to help you. And domain and range is something that people struggle with a lot. We're going to talk about it over and over again in this chapter. So today, maybe make a graph, but start thinking about, what if I didn't want a graph? Let's do another one. How about this function? Who remembers what this looks like? Find the domain and range of the function f of x equals 2 over x. This is a rational function. Oh, I think we're going to have some asymptotes. Again, if we think about domain as being what x is not allowed to be, just looking at that equation, what could you tell me I'm never going to be allowed to have as x? 0. Do you agree with that? I can't put 0 in my denominator. So these are some things you should start looking for. Square roots. You can never have a negative under a square root. Fractions. You can never have 0 in the denominator of your fraction. So those are some like key things that should stick out of my domain is not going to be all real numbers. So right away I know x can't be 0. Let's see if that's the only value here. Let's just make a little xy chart again. If all else fails, if you ever forget how to graph something, you should always think about xy charts. And I'm just going to pick some points here. Stop me if you're confused on where I'm getting these. But if I pick negative 2, I'm going to get 2 over negative 2, which is negative 1. If I pick negative 1, I'm going to get 2 over negative 1, which is negative 2. Can you have negatives in the denominator? Negative exponents, right? We don't want to have negative exponents left in your answer when you're talking about letters with exponents. But negative numbers are totally allowed in the denominator. 0 is the only thing that's not allowed in the denominator, because if you divide by 0, your calculator might blow up. There's a good chance. Be careful if you try it. It'll probably just say error. But if you do it enough times, you never know what would happen. Zero. I can't get a value out when I plug 0 in. If I plug 1 in, I'm just going to get 2 over 1. If I plug 2 in, I'm just going to get 2 over 2. Yes? We'll maybe think about some other points here. -2, -1, -1, -2. 0, I have nothing. 1, 2, 2, 1. Man, what kind of graph is that going to be? What if I picked 5 for x? What would I get? What if I picked 100 for x? What would I get? That's okay. You don't even have to simplify it. You can just say 2 over 100, right? What if I picked 1,000 for x? What's happening here? As x keeps getting bigger and bigger and bigger, what's happening to the y values? Smaller, smaller, smaller. Am I ever going to get this side to give me a negative y value? Am I ever even going to get this side to give me 0? 2 over a million, 2 over a trillion, 2 over whatever comes after a trillion. Really, really small, but not actually 0. Remember, that's the idea of an asymptote, which means this side of my graph is going to keep getting closer and closer to 0, but it's never going to actually touch 0. And if you think about plugging in numbers this way, if you pick numbers between 0 and 1, when you divide by a fraction, that's the same as multiplying by its reciprocal, so you're actually going to get bigger and bigger numbers. Like if you pick 1/2 here, 2 divided by 1/2 is really just 2 times 2. And if you pick 1/10 and 1/100th, you're just going to keep getting bigger and bigger numbers. So this side's going to keep going up like this. You kind of remember these shapes now? They're very symmetrical. So this side down here is going to do the same thing. This side's going to go down. And this side's going to be like this. They're kind of weird at first, but the asymptotes really help you kind of know how to draw your graph. Usually you want to make sure that it is opposite, because sometimes it's side by side. You have to be really careful. But yes, it's usually very symmetrical. So we said the domain, we knew already that x is not allowed to be 0. Is that the only value I would never be able to get for x? Is there any other restrictions on my domain? I think I agree with Sean. I don't think there's anything else I'm not allowed to have. This side of my graph will have every positive x values. Every value getting closer and closer to 0, every value going out this way. This side of my graph is going to include all negative values. The only value I'm not allowed to have is 0. So interval notation is kind of messy here. We have to say we can have everything from negative infinity to 0, not including 0, and from 0 to infinity.
I thought that was the or sign.
It kind of is. This just means both at the same time, like this or that, which is kind of true, right? I don't know. Sometimes you can make an upside down one like this, which means the intersection of both of those, but they don't really intersect, so I don't know. Right, just use and then, I don't care. Set notation might be easier on this one. When there's just one number you're not allowed to have, you can say x can't be 0, but it can be everything else. So the way that you write that is you say x cannot equal 0, which might be a little bit easier. I know, they're just scribbles. I think I was in college before I actually could draw one decently. What about the range on this one? And again, when you're thinking about domain range, you want to think about what am I not allowed to have, or what will I never get out of this? So when I look at this graph, looking at these y values, do you agree that this is going up towards infinity? Like all these big numbers will all get chosen? And this is going down, so negative infinity is all getting chosen. So is there anything I'll never be able to get from my y values on this one? Yeah, and if you remember, we actually talked about horizontal and vertical asymptotes when we talked about these graphs. This graph has two asymptotes, the line x equals 0 and the line y equals 0. It's never going to touch either axis, so the point 0, 0 will never be included. So my range is exactly the same thing, negative infinity to 0, 0 to infinity. Or you can say y, because it's the range, such that y is not allowed to equal 0. I don't care which way you do it. Continuity, whether something is continuous or not. This is something that we didn't really talk about last year. This is kind of a new concept, but a nice definition of whether a function is continuous is if you could graph the function without ever lifting your pencil up, that's a continuous function. So give me a function that we know that's a continuous function. X equals y, or any linear equation is a continuous function. Any parabola is a continuous function because you can draw it without ever lifting your pencil up. So looking at these graphs here, these are some special types of ways that it's not continuous. This is a nice little polynomial function. Continuous at all x values because there are no holes, there are no gaps, there are no asymptotes. Which means if you have any of that on your graph, it is no longer a continuous graph because you would have to lift your pencil up to graph it. What your book cares about is maybe knowing the labels for these. So there's two types of removable discontinuity. Removable discontinuity is a type of discontinuity where you could fill in the gap or the hole with 1 point. An example of that would be like a hole in the graph. And they give us two different types here. One type is right here, where you have a nice little graph, and then this part has a hole, which means it's not defined, and then it keeps going. But notice it has a little point up here that is defined. That's kind of a weird little piecewise function. This is called removable because all I'd have to do to make that a continuous function, if I was allowed to, is I could take that little point, and if I just moved it down there and filled it in, do you agree that would now be a continuous function? That's what it means to be removable. You could fix it with 1 point, like one little dot of your pencil, and you could fix it. Are you allowed to do that? No. But hypothetically speaking, that's what we're talking about. Yes. Well, we talked about these last year. X squared minus 9 over x plus 3 is an example of a graph with a hole in it. Because if you factor the top, you can cancel that out. And if you can cancel out what the bottom part is with the top, you're just left with a line, x minus 3, but it's still undefined at negative 3. And so that would be an example of a hole in your graph. Like it would look like a straight line with a little hole in it. There's also piecewise functions, which I don't think we ever got to last year, and we're going to do that later this week. And that's another example of a type of function that could have a hole in it. This one is also removable. The difference between this one and this one is this one had that little point already up there that I could kind of just slide down, but it still has just one hole in it. Instead of being able to slide the point down, I'd have to just fill it in with my pencil, but still it's removable because I could fix it with one point, one dot. A jump discontinuity is I think, self-explanatory. It jumps. Like if you were drawing this graph, you'd have to stop and jump up. So it's a jump or a gap in your graph. A step function is an example of that. We did that last year, it was very early on, like chapter 2. I think you did. It's just chapter 2, a long time ago, like a year ago. Infinite discontinuity is an asymptote. If your function has an asymptote like the one we just graphed, then you would have to lift your pencil up. On your homework today, I think they might ask you like to label what type of discontinuity it is, and these are the different types that we would be labeling. Okay. And so this one is a really easy example here. I only put it on here because I was printing these out for you. But which of the following figures shows functions that are discontinuous at x equals 2? The parabola or the line? Yeah, the parabola is continuous. We would never have to lift our pencil up. But this one, we have a problem right there at x equals 2. And what type of discontinuity would that be? A hole, but more specifically, what does the book call it? Removable. I always want to put an E in that, but it's not. Increasing and decreasing functions and max and min. That's the last thing I have to talk about. And I feel like we talked about this a lot last year, especially with polynomial functions, but I don't know if you remember or not. But an increasing function, the book defines it as a positive change in x results as a positive change in f of x, or y. I like to define it as x gets bigger, y gets bigger. Or if you're thinking about walking on your graph from left to right, it would be like walking up the graph. For undefined, right? A decreasing function, again, we can define it very mathematically. A positive change in x results in a negative change in y, or f of x. Or, as x gets bigger, y gets smaller. It's smaller, I need another s in there. A parabola is a great example of this. If I was walking on this graph from left to right, maybe. Okay, if I was walking on this graph, it would be like I was walking up the graph. It's getting bigger. It's increasing from here to here. But then as I turn the corner there, I would now be walking down the graph, kind of like downhill. Or if you think about this as x is moving to the right, or as x is getting bigger, the y values are actually falling now. So this side would be decreasing. Right? Memories of the increasing, decreasing? And constant is just if it doesn't change at all, right? I'm not even going to write anything out on that one. That would just mean if the y is not changing at all, like a slope of 0. So on the next page, I copied some pictures for you from your graph, from your book. On your homework today, they're going to ask you to say the intervals where it's increasing and decreasing. I gave you some examples here that it's always increasing. Like this lovely function right here, we could say it's increasing on the entire x value. So we could say from negative infinity to infinity, it's increasing. And this is a lovely little graph that's decreasing the entire time. So this would be decreasing from negative infinity to infinity, and constant from negative infinity to infinity. This is like what you're going to see on your homework, a graph that's not constant or increasing or decreasing the whole time. And they want you to give the intervals. And they're talking about the x value intervals. I don't care what's happening on the y-axis. I want to know where is it increasing or decreasing on the x values. So if you look at this, it's decreasing from negative infinity, so coming in from the left, all the way to right here, which is negative 2. So they give that lovely little interval there. And then it's constant from negative 2 to 2. And then it changes to increasing from 2 to infinity. They include the endpoints. We'll talk about this a little bit more. I feel like it shouldn't include the endpoints because at negative 2 and at 2, how can it be both increasing and constant at the same time? I feel like those should be parentheses. But obviously, I'm not going to be too picky on that since the book uses brackets, and I would choose parentheses. So what if I gave you one like this that's a little bit harder because it's a rational function? And I said, tell the intervals where this function is increasing and where this function is decreasing. And they give you the graph up there. If we graph x squared over x squared minus 1, you'd have two asymptotes. So see, we have asymptotes here and an asymptote here. I was trying to make a dotted line for an asymptote. I want the intervals on the x-axis of where this is increasing or decreasing. You can do this however you want. I tend to start from the left side of the graph, so I start with negative infinity and work my way towards infinity. And if I start over here and I look at this little section of the graph, is this little piece increasing, decreasing, neither, both? I think it's increasing. If we started walking along here, it's a very subtle change at first, but as x is getting bigger, do you agree that y is getting bigger? I'll be like walking up the graph, that'd be kind of hard thing to walk up, but it's increasing from negative infinity to, yes, to 0. What do you think about that? So, again, remember that we're working with the x-axis here. You're right, this side's still going up, but Tyler kind of jumped on over to the next section. He said, okay, this is increasing the whole time. What's next on my graph? I have to get over the asymptote, and then look at this section. From where this starts on the other side of the asymptote all the way to 0, do you agree that that's increasing also? So could we just say all in one interval that it's increasing from negative infinity to 0? Well, there's not an asymptote at 0 on this, right? You're right, there is an asymptote at negative 1. And so you could say, I don't know. I think that this is totally acceptable to say negative infinity to 0. If you wanted to say negative infinity to negative 1, and then from negative 1 to 0, because you're saying the asymptote shouldn't be included, right? I get that, and I agree because the asymptote isn't part of my graph. But because we're just looking at like the domain values, that's why this is okay. But I would never mark that wrong either. Does that make sense? Like both would be acceptable answers. What about the rest of my graph? If I go from here down, since the word down there, do you agree that this part of my graph is decreasing? What about the other section up here? After I jump over the asymptote, what about this section? Which means if this was increasing, do you agree that this side is decreasing if I was walking on this graph? You have to think going from left to right. Maybe, it's pretty steep there. But I think we could say it's decreasing from 0 to infinity. Or, like Sean said, we could say from 0 to negative, no, this one would be to positive 1, right? And then from 1 to infinity, because you're not including that asymptote, which is totally okay to do it that way. There's definitely one on your homework like this. We'll come back to that tomorrow. All right, look, the last thing, you don't even have to really write much down here. We talked about max and mins a lot last year when we talked about polynomial functions. And I just want to point out two things here. One, make sure you know the difference. A maximum and a minimum is a turning point in your graph. So if you have a maximum, actually I'll just draw a little graph here. Right, a maximum is like a high point in your graph. It occurs where it changes from increasing to decreasing. So like right here would be a maximum, right here would be a maximum. Last year we only talked about local maximums, and I want to point out this other definition. A local maximum is just any turning point on your graph where it changes from high to low. An absolute maximum is the highest point on the graph. So if I say what is the absolute maximum, it's only one. Like what is the highest point? And sometimes there might not be an absolute maximum. And the same thing with the minimum. A local minimum is just any low point on the graph that occurs where the graph changes from decreasing to increasing. That's all we talked about last year. But now we can throw in the fact that we have an absolute minimum, which would be the lowest point on the graph. My little graph up here, this has no absolute minimum because these arrows keep going down forever, which means there's never going to be a lowest point on the graph. Make sure you have your assignment sheet. It's the next assignment. 1-2 day 1. See, I told you.